So when we're taking a look at this problem, basically we see that it says that when the y is 0, so whenever this is flat, the spring still has a force of 60 pounds, and that would be each. So that means that the force on here is going to be, since force is equal to Ks, the force is 60 pounds, K is 40s, so that means even whenever this is shrunk down to 0, that they are stretched, what is 6 divided by 4? 1.5. They are stretched 1.5. So our initial stretch is already 1.5 for this problem. So that's something important that we have to have going forward. Now, whenever we're going to pull away to a distance of y equals 2, when y equals 2, that means that if I'm looking at this triangle, why is it doing that? If I'm looking at this triangle here, that's a distance of 1 when y equals 2. And then this is a distance of 2 feet. Now I can tell, because I'm awesome at trig, that this is a 1, 2, square root of 3 triangle. So since this is a 1, 2, square root of 3 triangle, that means that they're, okay, so whenever this is flat, if I draw a picture of this one, this is flat. Why are you doing this? Stop it. When this is flat, then this is like that, then this is a distance of 2 feet, right? Because this tells me that this is 2 feet. So I'm stretched, my S right here is 1.5 when it's flat. But whenever it's stretched, whenever this is like all parallelogrammy, then this distance is the square root of 3. So the new stretch is going to be 2 minus the square root of 3. So that's 0.267. So this means that this is now being stretched an additional 0.267. There we go. So the new stretch length is 1.767 or something like that. Yes? Yeah. So I was at 1 point, so I'm basically going to say, okay, so what's 2? Well, I already did that. 2 minus that. So 1.5 plus that. So that's my new stretch length. So that means that the new force that the springs are pulling on, the new spring force, which is Ks, like the new S or S2 or whatever you want to call it, is now 40 times 1.767. So that's 70.7. So the new force is 70.7. So that's useful. The force is now 70.7. So that means if I look at this C here, for example, it's getting pulled in 2 different directions by these 2 different tensions. So it's getting pulled this direction and this direction, and it's getting pulled this way at 70.7. So whatever this angle theta is here, this will be like, say, T1, and this will be T2. Now they're going to turn out to be the same, but I don't necessarily know that yet. So that's angle, stop it, angle is theta. Okay. So if I'm looking at just this part, I can do a free body diagram, which I've done, and now I can do some of the forces in the Y. Will give me T1, and these are both going to be theta. T1 sine theta, and it doesn't even really matter what it is at this point. T1 sine theta minus T2 sine theta. And those are the only things going on in the y direction, so that equals 0. So that means that T1 sine theta is equal to T2 sine theta. And since theta is the same, that means that T1 is equal to T2. So that's kind of nice. That's going to tell me that the tension in all 4 ropes is the same, which is probably what you assumed anyway, but we actually proved it. Now I'm going to do the sum of the forces in the x direction. So I have minus 70.7, and now I have the cosine of t. Now I'm just going to call them all t, since I know they're the same. Call them all t. No, you don't go there. You go here. T. Cosine theta, and then another t cosine theta equals 0. Now I think I can figure out what theta is, yeah, because the tangent of theta, is opposite over adjacent. Wait, it's a 1/2 squared 3. That means 30 degrees. So 30 degrees. Amazing. Amazing what happens when you're brilliant. Okay, so that means that twice t cosine 30 is equal to 70.7, and since cosine of 30 is the square root of 3 over 2, the 2's actually end up canceling out, so I have t equals 70.7 divided by the square root of 3, so divided by the square root of 3 is 40.8. So I have t, the tension is equal to 40.8. Is that what I'm actually supposed to be finding? Determine the magnitude. Oh, so that's the tension. Now I have to find the force. Okay, so to find the force, what I'm going to do is now I'm going to focus on this knot right here. Okay, so that knot right there. So if you remember the picture, I have a force F, which is the force that I'm trying to find, and I have a tension here, tension which is 40.8, and I have another tension here, which we're going to call T3. Now, by the same logic as before, let's see, so the angles here, this is going to be 60. Okay. By the same logic as before, because those are the smaller ones were 30. So, by the same logic as before, the sum of the forces now in the x direction are going to be negative 40.8 times that would be the sine of 60, and then plus T3, okay, plus T3 times the sine of 60. And that's going to be equal to 0, which again is going to tell me that T3 is equal to 40.8. So this isn't really T3, this is still 40.8. So now I can sum of forces in the y, and I've got that 40.8 sine of, not sine, it's only cosine 60, minus another 40.8 cosine of 60. Plus the force going up is going to be equal to 0. So force is going to be equal to twice 40.8 times the cosine of 60, which is 1/2. So I'll just write that so you don't freak out. Okay, so since the cosine of 60 is 1/2, then the 2 and the 1/2 is just the 2 cancel, and I get that the force is equal to 40.8. This is pretty cool, or pounds, or whatever it is we're doing. But the only reason, well, this math will always work, it just accidentally happens to be the same number because we got a 30-60 triangle. In normal triangles, it's not going to do that, so that'll be fun.